today's lesson, we are going to continue to look at functions or relations and functions. And now we're going to be looking at a way to characterize or describe these functions. And we're going to be using domain and range. So we're going to learn what domain and range are. We're going to look at examples of how to write it and how to identify the domain and range for each or for different functions. So if you want, in class, we're going to do a little bit of a warm-up. You can try this at home if you want, but essentially it's going to be kind of a reverse style of Pictionary. So one partner is going to be given a picture and they have to describe it to their partner and have their partner try and draw it exactly. So you can take a look at some of these examples, right? So if this was an example, I might say, okay, you're going to put a point at x is a point at -2, -1, right? So describing where this point is. This point is at -2, -1. Or you can say, I'm going to draw a line. It's going to be at -1 below, or at a y value of -1. And it's going to start when x is -2. And you're going to go in the positive direction. It's going to be a horizontal line. You're going to go in the positive direction forever. Right? The arrow kind of indicates that it's going on forever. Right? So different ways you might try to describe to a person what this graph is. Right? So you might talk about the starting point, the heights, the horizontal starting points, the vertical starting points, things like that. Right? How long you're going for, where you're going, or where you're headed towards, that type of thing. Right. So with a partner, you would try these different ones, try to describe these relations so that they could draw it. Now, different ways you might do that, right? But you can see that they do get a little bit more complicated. So if you were to try this, right, this one's different, like it has two circles at the ends, there's no arrows at the end, right? How would you describe to a person how to draw these images or like these relations? What strategies would you use? Right? So you can think about it, right? But the whole idea is that you might talk about in terms of vertical restrictions and horizontal restrictions, like where does the graph exist horizontally, where does it exist vertically, things like that. And that's kind of what domain and range is. Because domain and range refer to horizontal and vertical components of our relation. Before we get into that specifically, we want to talk about the different types of numbers just to get an idea of what we're referring to. Right, so I have here a number line, -10, -9, going all the way up to +10. Right, so you might have learned this going back into grade 9, the types of numbers that are positive and negative and 0. And these values are integers. When we're dealing with values, so let's say 1, 2, 3, 4, 5, and so on, going upwards from there, right? So only the positive values, these are natural numbers. And here we have kind of a combination. So we have 1.5, -12.3, 99, the square root of 2, pi. So these are all different types of numbers. And these are examples of what we call real numbers. So what do these terms actually refer to? Well, real numbers are all numbers including fractions, decimals, and roots. So any number you can think of is going to be a real number. Natural numbers are our counting numbers. Integers are our positive and negative whole numbers. And some other terms that we're going to be looking at. So this little symbol here, it looks kind of like a fancy E, right? If we're trying to write it, it might look something like this, right? Kind of like a weird E, almost like the end of a pitchfork type of thing. This is actually the Greek letter epsilon. And mathematically, what this value or what this letter or Greek letter refers to, this basically just means belongs to. So for our purposes, when we're referring to or using this Greek letter, we're using it to say that an unknown value belongs to one of these number families, right? So it belongs to one of these number families. And a straight vertical line, mathematically, in our notation, what this is going to refer to is, so a straight vertical line refers to, so such that. Right, so the Greek letter epsilon means belongs to, and then this vertical line means such that. So basically, it's going to be kind of giving restrictions to what our values could possibly be. So domain and range, what does that actually mean? Well, for any relation, the set of values of the independent variable, or the x values, is often called the domain of the relation. So when we're referring to what the possible x values are, we're referring to the domain. When we're dealing with the dependent, or the y values, we are talking about the range of the relation. So y values are range, x values are domain. Right? One thing to note, for a function, for each given element of the domain, there must be exactly one element in the range, or exactly one element in the range. This is kind of going back to the previous lesson that basically said, for a function, every x value has only one y value. Right? You're just going back to that definition. So when we're turning it into domain and range, for every element of the domain, or so every x value, there's only one y value. Just a different way to refer to that. When we're writing the general notation for domain and range, it's going to look a little bit kind of weird, but it's going to take into account kind of everything that we kind of talked about. Right? So for domain is referring to the x value. So what we're going to do is we're going to use squiggly brackets, and this is going to refer to, squiggly brackets mathematically allow us to refer to a set of values. So a set of values, we're going to say the x values. So the set of x values for our relation, whatever they happen to be, belong to, so epsilon, and we're going to use this little r symbol. So it's almost like two lines, and then the rounded part of the r. So x belongs to, let's write this in a different, so x belongs to the r represents any real number. It represents the family of real numbers. So x belongs to, we'll say, real numbers, and then we're going to draw a line. So x belongs to real numbers such that, and then here's where we usually have our restrictions of what x is allowed to be. The general notation is we'll have a one value greater than or equal to, or less than or equal to x, which is less than or equal to another value. And then we kind of close it off. And here we kind of have where we put our minimum and our maximum values. So this would be kind of saying x is, or x belongs to real numbers, or x is any real number such that x is above or greater than or equal to a number, but less than or equal to another number. Right? And this second section here, this portion here, will vary depending on what our function or what our relation looks like. For the range is going to have a similar notation, except instead of x, it's going to be y. So y is any real number, or belongs to the family of any real numbers, such that, and then we have our restrictions. So where does the y values exist? Between what values? So it's very similar between the two. It will take some time getting used to, because it is a different format, a different style of, or different way of writing things that you might have been used to, but hopefully once you look at some examples, it becomes a little bit easier to understand kind of where or how we can determine the domain and range. So we're continuing. So when we're talking about domain and range, right, we need to kind of know what the possible values of x and y are for domain and range. And one thing to note, when we're looking at graphs, if it has arrows on the end, depending on what direction they're heading, it means that you're heading towards infinity, right? Or the arrow means the line or the relation or the function is going to continue on forever. So if the line continues on forever in this direction with an arrow, it's headed towards positive infinity. Going up in this direction, it's negative infinity. Down here, it's negative infinity for, well, it depends when if we're talking about domain or range, right? So just different things to keep in mind, right? Where is the line headed? Where are the values that it's headed towards? So you have to kind of think about that when the lines have arrows at the end. So let's look at an example. We'll look at the first one here. So we want to state the domain and range of each relation. So here I have my relation. We have arrows at the end. Draw it in. We have our line. And here. So for our domain, we're going to start with domain first. Domain, again, refers to our x values. So I'm going to go and have at least set it up. So I'm going to say x is any real number. We're usually always going to start off like that. X is any real number such that, so our vertical line, and now we're going to state our restrictions. So if I look horizontally, right, because domain is going to be left and right. And if you have to put that down as a reminder, or when we see domain say left and right, that's fine as well. So if I look at the end of my function here, right, I can see there's an arrow at the end, so that means it's going to continue on in this downwards direction forever. So what are the x values? What are the horizontal values going to be when we continue on in this direction? Right? Well, if we continue down, or if we look at the scale up here, we see that they're getting more and more negative as we go, right? And the arrow means it's going to continue on forever. So if we head in this direction horizontally forever, we're headed towards negative infinity. So we could say that our minimum value for x is negative infinity. So we can say x is going to be greater than or equal to negative infinity, but less than or equal to, and then our maximum is going to be looking at the other direction. So we see that we have an arrow on the other side. So if that continues on upwards, and we look horizontally at the x values, okay, the x values are increasing, so they're going to be getting more and more positive. We're going to continue on forever. So we're going to be headed towards positive infinity. So this is basically saying that x is any real number such that x is between negative infinity or positive, and is greater than negative infinity but less than or equal to positive infinity. So if we think about what does that mean, well, that means x can be any possible value. So an easier way, if that's the case, where it's positive and negative infinity for your maximum and your minimum, your highest and your lowest possible values, you can just write x is any real number. Because essentially what that's saying is that there are no restrictions for what x can be. X can be any number that you think of. If we look at the range, let's do the same thing, except range is now going to be the vertical values. So instead of x, it's going to be y. So we can start off y equals, or y is any real number such that, and now let's look at the vertical components. So let's look at the lower end on the left end, right? So on the left end, the lower end of our relation, again, we have the arrow. It's going to head downwards forever. That arrow means it's going to continue on forever. So if we go downwards forever, what values are we headed towards, or what's my lowest possible value? Well, if it's going down forever, there's no end. My lowest possible value is going to be negative infinity. So that is my lowest possible value. So y has to be greater than or equal to negative infinity. Is there an upper restriction? What is the highest possible value or y vertical value or y value my function or my relation, will be. Well, again, we have an arrow on the other end. So that's going to head upwards to the right forever or towards positive infinity. So y is any real number given that it falls between or is greater than negative infinity but less than positive infinity. So there are no restrictions really on what the y values are. They could be any number you can think of. So an easier way to represent that would just be to say y is any real number. There are no restrictions really for x or y in this case because x and y can be any possible number you think of. Any possible number you can think of for the domain or range, there's going to be a value existing there on this relation. Now that's not always going to be the case, right? So there are going to be some situations where for our relation or our function where there are restrictions. So it's going to look a little bit different. So let's look at this example here. Let's look at a parabola. So this U shape here. So when we're looking at here, right? If I'm looking at start at our domain. So for our domain, again, the beginning is going to always roughly be the same. X is any real number, so X and then epsilon, and then that R, X is any real number such that, and now we're going to put in our restrictions. So again, if I'm looking at the ends, I see arrows, okay, so that will tell me for my domain, or when I go left and right, I can see that I have an arrow on the left or on the one end, right? So basically, if you think of like a vertical line, kind of like a vertical line test, but not really, we're not testing that. But if I bring a vertical line over, okay, I have on my left side, I have an arrow. So for domain, that arrow means that is going to continue up and out forever. So that means my lowest possible value is going to be negative infinity. Filling it into my notation. And if I continue with that vertical line, okay, just moving it over, all I'm doing is just seeing where does this function exist horizontally. Okay, I can see that on the far right side, or where the last values that I can see for my function, it ends with another arrow. So that means it's going to continue up and over, and that means that the highest possible value in terms of x is going to be positive infinity. Now we kind of had an example like this already with the last one where we could say, okay, instead of writing this whole long thing, I could just write for domain that x is any real number. Range is going to be a little bit different. So range, now we're going to look vertically at our vertical values. So let's start at the bottom. We want to start at our lowest or the most negative and go to the top. Right? So before we get into the actual values, we should actually just start off the same way. So squiggly line, y, epsilon, r, and then a line. So y is any real number given that, and now we're going to find our restrictions. So if I start at the lowest possible value, I'm going to take a horizontal line now because we're dealing with just to kind of visualize it. So the lowest possible value here, right? We see the parabola come down, it reaches this vertex and then goes back up. So the lowest possible value here is -1. So -1 is the lowest possible value. So y has to be greater than or equal to -1. And then we go to the highest possible value. We see there are arrows on the top points here. So that means it is going to continue upwards forever. So our highest possible value is going to be infinity. So that means that y is any real number given that y is greater than or equal to -1 but less than or equal to infinity. Now really anytime one of these sides has infinity, what we can do is we can really just not include that part. So another way that we could write this, y is any real number given that y is greater than or equal to -1. We don't need to include the less than or equal to infinity because that doesn't really give us any more restrictions. There's nothing, or there's infinite number of possible values. It's not like a firm cutoff for y has to be less than this value. So in our third example, this sine wave, let's go through and try to do this a little bit quicker now that we've done a few. So we're going to start with domain, squiggly line, x is any real number, given that, and now let's look for any restrictions. So now I'm going to take a vertical line just to visualize it a little bit easier for the horizontal value. So x, the lowest possible value, so is this end of my function here. Well, there are no arrows on the end. So I'm assuming, based off of this graph, it does not go any further than that point. So that means that the lowest possible value here, if I look at the x values, is 0. So 0 is the lowest possible value. So that means that x has to be a value greater than or equal to 0, but less than or equal to. I'm going to take my vertical line and move across my relation until I get, or if I come in from the right side, the highest possible value is, for all intents and purposes, we'll say it is 360 degrees, where it should kind of cut off. So we'll say that our function, or the domain for our function is, domain for our function is x is any real number, given that x is between 0 and 360 degrees, or x is greater than or equal to 0, but less than or equal to 360 degrees. Our range is going to be similar. Y is any real number, given that, and we're going to come up from the bottom for our lowest part. The lowest possible value for y, we come up, we see it's at -1. So -1. So y is greater than or equal to -1, but less than. And then the upper limit, if we come down from the top, is +1. So y is any real number, any possible value that we can think of, as long as y is between -1 and 1. Right, so what we're doing is we're essentially thinking about, imagine putting imaginary horizontal and vertical lines across the top, or the highest part of our relation, the lowest part, right, coming in from all sides and saying, okay, what are these possible values, right? Or what are these kind of restrictions? Domains for the horizontal or from the x values, and range coming from the top and the bottom. Domain left and right, range top and bottom. Right, so different ways you can think of it. This next one, again, we're going to start with domain. Domain, we're going to come in from the left, okay. Lowest possible value in terms of x is going to be 1. So when we start off our domain, x is any real number, given that, and x has to be greater than or equal to 1. So 1 is going to be our low value. Now we need to think about what our high value is. So if we come in from the other side, we see that, oh, okay, well, there's an arrow here. So that means that it's going to continue on forever. So that means it's not actually ending here, it's ending infinitely somewhere down the line. So I could say that x has to be less than or equal to infinity. Doesn't really help us, right? It doesn't add any more specifics to this. So I'm just going to get rid of that part. I don't need to include that portion when there's infinity involved. It doesn't really restrict it any further. So this is the same thing. Y, or x, is any real number, given that x is greater than or equal to 1. Because again, we can see this lower restriction. The x value is not going beyond that point. For the range, we're going to do the same thing again, except instead of x, we're going to look at the y values. So y is any real number, given that. And let's find the minimum possible value. So again, minimum value, we come up from the bottom. We see that the range or the y values are not getting any lower than there. So that is going to be my minimum or my lowest possible y value, which in this case is 0. So y has to be greater than or equal to 0. But what is the upper limit? So if I come down from the top, again, I see an arrow. I reach an arrow. There's not an endpoint. That arrow is going to continue on forever. So that means that the y values, the upper level or the upper limit is infinity. So to say that y has to be less than or equal to infinity doesn't really add any restrictions, so we don't need to worry about adding in this portion here that would look like this. We don't need to worry about adding that because, again, it's assumed if we don't have it there, that's kind of the upper level. Like y will continue on forever. So y has to be greater than or equal to 0, which is the same thing as greater than or equal to 0, but less than or equal to infinity. Now, every example we've looked at so far has dealt with graphs. And it's going to be slightly different when we look at something else, where we look at a table of values, a mapping diagram, or points. And the difference is we can't make assumptions that this relation or this function is going to exist at values in between what is shown. Right? So here what we're seeing is x is 0, y is 2, x is 3, y is 4. X is -3, y is -2, and so on. Right? We don't see anything in between those possible numbers. We don't see between, right? If I was to plot these points just hypothetically, okay, so 0, 2 is here. 3 and 4 might be up here. -3 and -2 might be down here. And then 2 and 4 would be up here. There's nothing in this table of values to suggest that these points are connected, right? That the relation is a line going between all 4 of these points. For all we know, based off of what's given to us, it's just these 4 points. Right, so here we can only assume that it's only points. We don't want to make assumptions, or sorry, not assume. We're only going off of what we know, and that's the 4 coordinates. We're not making assumptions that the relation connects all of them, or there's an equation that goes through all those points. We're only focusing on what's been told to us, which is only these 4 values. So because of that, it's going to be a little bit different. It's actually going to be a little bit easier. Anytime we're given a table of values, all we're going to do is literally list the specific values. So domain is again the x values. So the domain is just going to be 0. I'll make it I'll do it in order. So -3, 0, 3, or 2, and 3. So I don't need to say x is any real number because it's not. X is not any real number. X is only these specific values. So when we have a table of values, all we're going to do for domain and range is literally list the x values and list the y values. So for range, I'm going to list the y values. So we have the lowest -2, 2, and 4. Now, even though 4 comes up twice here and here, I don't need to relist them or list them twice, right? Because it's just y is 4. Y could be 4. I don't need to say y could be 4 and it could also be 4. So I don't need to list it twice if we see it come up more than once. So the y values or the range can only be -2, 2, and 4. Again, we're not making assumptions that it exists in between those values, even if we were to connect them with a straight line. Last example, so mapping notation or a mapping diagram. Same idea, right? We can think of the first values of x or domain, second values or second column as y or the range. And when we have something like this, we treat it similar to a table of values. I'm just going to go through for my domain and write down all the values that are listed. So -1, 0, 1, 2, 3. Those are the only values that we're assuming that x could take. So our domain is only those 5 possible values. For range, same idea. I'm just going to list the possible values: 3, 5, 11, 21. That's my range. Those are the possible values, the only possible values that y can take for this relation. Right? Doesn't matter if it's a relation or a function. It's just what are the possible values. So the whole thing that we looked at in the previous lesson of whether it's a function or not does not apply to domain and range. You can do the domain and range for a function. You can do the domain and range for a relation that is not a function. The main thing is that if you're looking at a table a graph, we have kind of a specific format to follow. We're kind of looking for the upper and lower limits or restrictions for the x and the y's, x and y values. When we have a table of values or a mapping diagram, we're just listing the possible values. So the main things are, it's going to be a little bit tricky to get the notation down, but just as long as we remember domain is the x values and range is the y values, that's a good start.